Okay, class. Now let's talk about the non-conventional, no, non-traditional, or sometimes people like to call modern optimization methods. There are many, but the most famous one is genetic algorithm and also the famous thing is simulated annealing and ant colony optimization or particle swarm optimization, and there is also neural network based optimization, and they tend to include the fuzzy system here, fuzzy based optimization. Most of these algorithm or methods are from biology. Genetic algorithms are mimic our process of evolution of genes, genomes, chromosome, and all this biology thing. We are trying to mimic this behavior of genes and their evolution, and utilizing this evolution, we are trying to optimize something. That's a genetic algorithm. And simulated annealing is a kind of physical process. And do you know what annealing is? Do you know what the annealing is? It's some specialized process. You know, when you heated steel pieces very high temperature, and if you put that heated steel plate rapidly into the water, what will happen? The metal grain becomes larger, and those structure will make this metal more stiff. It's a kind of heat treatment process. The reason the metal crystal becomes larger is while in high temperature, metal molecules are vibrating more rapidly, more actively, but when it cooled in very fast time, the metal molecule don't have enough time to go back to its optimal point. I mean the least energy point. So the other approach of the heat treatment is heat it up and very slowly let it cool. That is annealing. Okay? So artificially agitate and then let each of the molecule go back to its most least energy point. The idea comes from this annealing process, so that's why we call this a simulated annealing. Okay, like the annealing, we need to agitate it. Agitation means for the steel, it is just heating up, but in optimization, we are just arbitrarily put some different type of agitation. But anyway, the idea came from the physics of the metrology. Number 3 is ant colony optimization. You know, each of the ants are not that smart, but when they flock together, they tend to find the optimal path from their nest to the food source. How? They send out the scout ants, and when they come back with their own information, they share their information, and then based on this interaction of the information, they tend to find some kind of optimal path. Very similar. Swarm means large population of insects or school of fish or flock of bird or and the like. A swarm of bees or something like that. They also, the individual insects are not that smart, but putting them together, and if they make a swarm, the swarm can be much more smarter than each individual because of some specific behavior among this swarm. So mimicking those swarm dynamics, we are utilizing those biological behavior to make the optimization. That's a particle swarm optimization. And number 5 is your neural network based optimization. You know, the idea is also from neurology. You know, our brain is nothing more than a group of neurons. And this neuron is a one single cell, and it is very simple. However, the intelligence came from how these simple neural cells are interconnected each other. By mimicking their wiring system, we can do much more complicated and smart thing. That's the idea of this neural network-based optimization. And number 6 is the fuzzy-based optimization. It's not like the biological system, but however, I think this term is very famous nowadays. You know, sometimes it is not even possible to formulate your problem mathematically. Sometimes your only design requirement or objective function are only given as in linguistic form. And sometimes it's not possible to transform this linguistic form into mathematical form without help of this fuzzy system. And you know, nowadays many systems, usually white electronics, like your freezer, rice cooker, and microwave are all equipped with this fuzzy-based system. Okay. Anyway, these are the typical and most famous modern optimization techniques. And today, I'd like to talk about the genetic algorithm. And unfortunately, we don't have enough time to cover everything in these courses. So I will try to cover number 1 and number 5 and 6 And if we have some time, I will do about particle swarm optimization. Okay? Okay. Now let's talk about the genetic algorithm. Okay. There is a one, it is written in your lecture note, which will be distributed right after this course, class. In the Goldberg wrote a very famous book. It's titled like Genetic Algorithms in Search, Optimization, and Machine Learning. And this man is called as the father of this genetic algorithm. He's the professor in civil engineering department in the University of Michigan, and another guy in electronical engineering department, also professor in psychology department. Dr. Holland is also a professor in the University of Michigan. These two guys do a very fundamental job in this genetic algorithms. Anyway, thing is like that. You know, have you ever read the book named Selfish Gene? 이기적인 유전자? Yeah. What do you think? Idea is exactly the same. There is a gene. Specifically, we call it chromosome. It's a one single string of bioinformation, and group of this chromosome we call gene. So the approach in genetic algorithm is transform our problem into chromosome. Okay? And the next step is let these genes follow the evolution process. And you know, the key word in evolution process is the survival of the fittest. So the survivor will be the fittest one, which is in turn the optimal one, based on our definition. That's the whole idea of this genetic algorithm. Okay. From these two simple fact, we can deduce that we need some number of population, because a single entity cannot do anything in terms of evolution. Okay, right? There are several similar things, so this genetic algorithm requires population, n number of population. Okay? And since this evolution is kind of a random process, you know, we don't know which one will happen exactly. So it's we call it one of the stochastic process, and since we are dealing with the evolution process, we are doing exactly these three things. Survival test. Since we call survival of the fittest, so there must be some way to evaluate the fitness. So which is, in optimization, the objective function. Okay? Also, evolution, we have to think about this mating, or sex, or crossover. Okay? And a very important thing to consider in this evolution process is the mutation. Okay? Okay. If we can do these things, then we can make things be optimized. Okay, let's talk about some example. First one first, chromosome. If we have the n number of chromosome, we call it a population. And about the formulation, this chromosome is not the objective function. It should represent the solution itself. Okay? So single chromosome should be able to express all the possible solution. Okay? The fitness function is the objective function. Okay? Okay, let's make some example. The famous bean packing problem. Okay? These are one example of the bean, trash bin, like this. Okay? So let's assume there is a bin, an empty container. And let's call this as a container 1, container 2, container 3, and container n. So we have n number of containers, and let's say we have beans, not this bean. Okay? Okay? We have many beans, and each bean has its own identifier. So let's call this bean number 1, bean number 2, bean number m. Okay? Straightforward. And each bean has two characteristics, size and weight. So let's call this is a S size, S1. So bean number 1's size is S1, S2, Sm, and weight. So bean number 1's weight is W1 and Wm. And as you know, there is no exact beans. So this S, Si, and Wi can be arbitrary number in a given range, right? Some beans can be very light, some beans can be very heavy, while some beans are very large, but some beans are very small. And we'd like to put these beans inside of this each can evenly. How? Well, let's make up our own objective function. So let's say standard deviation of being i's weight. Oh, sorry. Bean's weight and standard deviation of bean's let's say volume minimize. Okay. Let's assume we are just distributing each beans into each of these cans, and we want to make it evenly distributed. So, for example, bin number 1 and some should be inside of this C1, and some other bins should be in here and there and the like. But the bin's weight is just the summation of the WI's inside of each can, each bin, and bin's size is the summation of this, just the bin's size inside of this bin. It's not very good naming. Let's call this as a can, because it's a bin and bin. Okay. So, can i's weight is defined as the summation of wj, which is inside of this can. And can's i's size is just summation of the size of the bins inside of this can. Simple, right? And how can you solve this kind of problem? It's a optimization problem. We'd like to minimize something, which is the standard deviation of size and weight. Okay? So, well, objective function is, because we have two things, standard deviation of weight, standard deviation of size, and we have to minimize these two things at the same time. So in this case, it is very straightforward. Let's say this is F1 and this is F2. Then we can just minimize F1 times F2, because we know that F1 are non-zero, non-negative value, and F2 is also non-negative value. And if we minimize these two, we are minimizing these two, right? Okay, you can make anything like F1 power to the A, F1 power to the B, based on your relative importance. Is the weight evenly distributed weight is much more important than evenly distributed size, then you can modify these two. Okay, anyway, basically we'd like to minimize this. Any questions so far? Okay, first step is to formulate this thing into the gene. Okay, as I mentioned before, each chromosome should represent the one single complete solution. So, for chromosome for this kind of problem should be like that. Chromosome is a single string of information. So let's say this is a chromosome number 1, and it has a array. It is an array or a vector. I mean, in terms of the computer programming, with size of m. Okay, so in each gene is the destination. For example, if B1 is the should be if B1 is inside of the can number 3, then it should be 3. 1, 5, or something like that. The value inside of this cell should be some value like this. So imagine that if you have this chromosome, can you recreate the configuration of this problem? If you have this information, can you find out how many beans inside of the can number 1, or how many beans in can number 2, 3, and weight of the can number 1 or size of the can number 1? Is it possible? Yeah, of course. So, which satisfy the problem is well formulated by this chromosome. With this single chromosome, we know that the one possible scenario is 100% described by this. Any questions so far? Design of this chromosome is not unique. It should be depend on the problem itself. But anyway. Okay, the next question is, how can we generate this initial distribution then? We can use random number generator. So initially, we do random number generator. So we can do it. For example, by random number generator, this one was happen. Every cell is filled with 1. What's the situation? All beans are in the first can, and the other cans are empty, right? What if this is n, and all these beans are 1? Then all bin number 1 to the bin number n-1 are inside of can number 1. And the last bin is inside of the can number n. That is also a possible thing. But anyway, this is not that good solution. Okay? So, thing is like this. Initially, you have to model your problem with this gene. Okay? Sometimes your gene is real coded gene. Which means these genes are real number or integers or something like that. or if for some different problems like your problem is an x, and this is an integer from 0 to 31. And if you prefer, you can transform it into the 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8 binary gene from 0, 0, 0, 0, 0, 0, 0, 0 to 1, 1, 1, 1, 1, 1, 2, 3, 4, 5, 6, 7, 8 binary gene. It depends on your choice. If this is more easier, you can choose each gene can only has the 0 or 1. Okay, binary number. But this one represents some value among 0 and 31, right? Like this. For those kind of problem, we can model it, but anyway, the important thing is that one chromosome should represent the complete solution. Okay? Okay. Is there any rules to design this chromosome? No, really. So, as long as your your chromosome completely model or completely represent the solution, then anything can be possible. For example, in your optimization, your situation is you have to deal with 3 different variables like x, y, and z. And the range is x is the real number from 0 to 100, or y is something like that. Well, I can use, first of all, chromosome with 3 cells, 3 genes, each assigned with x, y, and z. Okay, that is also possible, but it is not that good design. Anyway, or I can transform this x, y, and z into binary numbers. So assign, I don't know, in order to cover 0 to 100, how many bits do we need? But anyway, some bits are assigned to represent x, and the consequent bits are for y, and the other consequent bits are for z. That is also possible. Okay? I will explain why only these 3 genes are not that good design later. Anyway. Okay. Initially, design it and randomly choose the chromosome. I mean, feed it with a random number generator, and we got to make n number of same, not exactly same format, but different randomly generated chromosome. Okay? Okay. Once we make this n population, the next step we have to think about is function evaluation. Can you evaluate the standard deviation of can's weight and can's size based on this information? Yeah, of course. Why not? We know which bean is inside of the first can. We know which bean are inside of the second, and the like. And we know all this information. So if you write a computer program, then you can evaluate this one, standard deviation of can's weight and standard deviation of can's size. So you can easily calculate F1 times F2. Okay, so function evaluation can be done The other one is we have to think about the genetic operator. We have to make this thing to evolve. So this is function evaluation. We have to think about this crossover and mutation. Okay. Crossover we call mating. So it's nothing more than mixture of chromosome. For example, we have the 5 bits binary chromosome, like 10110. This is chromosome number sum, and this is I don't know, 10001. So for the crossover operator, what we have to do is first randomly choose 2 chromosomes inside of your population. You have n population, you're selecting 2 to crossover randomly. Okay? Okay, let's assume these are the chosen number, chosen 2. The other thing, the next step is randomly choose the location. Location, what I mean is we can, basically this sex or mating or crossover is the mixing of the genes to make a new generation, right? So how can we mix these 2 chromosomes? Well, we can first choose the location, but anyway, this is optional. So I choose 1, 2, 3. This location randomly, but you don't have to randomly choose the location anyway. You can just fix the location and then mix it. But anyway, if randomness in your operator increases, the possibility have global optimum will be increased. Okay, so I randomly choose it, and the next step is crossover. 1 0 1 0 0 0 1 1 0 1 1 0. So that's the new generation. And they happens to be the exactly same as their parents, which is sometimes true in real world, right? Okay, that's the crossover operator. You can choose multiple crossover point. So for example, you can choose randomly how many crossover points do you need. So if I select 2 crossover points and randomly choose the 2 different locations. So for example, if I choose here and here as the crossover, randomly chosen this crossover point, number of crossover points are also randomly chosen. and crossover points are also randomly chosen, then my crossover operator's result is 1, 0, 1, 0, 0, 1, 0, 1, 0, 1, 1, 0, 1. So this thing can be possible. And in the nature, sometimes this thing is possible. Self-reproduction, like a snail. You don't have two chromosomes to do the mating operator. Sometimes you can do the crossover operator with yourself, as is true in the real nature, where sometimes you need 3 chromosomes to do the mating operator, but there are many other possibilities. Yeah, that's the crossover. And mutation is, as you know, it's just random event. Some of your genes in your chromosome are just mutated. So, for example, 101101. Let's say this is one chromosome is. You just randomly select one chromosome. So this chromosome is selected. And then next step is you randomly choose which genes to mutate. So you choose this to mutate. If this is the binary chromosome, we run the random number generator once again, and we can change it to 100101. That is mutation. If our chromosome is real coded one, like this can packing problem, 317842, something like this, you can randomly choose which genes to mutate. 31742, and now we have to run the random number generator, and I don't know, maybe 7. That's a mutation. And by this mating and mutation and survival test, okay, let me explain the survival test once again. Survival of fittest, which means also the unfitted chromosome will be eliminated. So, most straightforward approach is, if you have n number of population, and if you can run this fitness test for each of this chromosome, and you can sort this chromosome. So, and you can set the standard for the survival rate. So if I design my program like the lower 30% will be destroyed, then among your, let's say this is a 10 population, the chromosome which has the lowest fittest value, 3 of them will be destroyed. And the next step, the upper 7 will survive, and the empty 3 will be reproduced by mating or mutation or just another initialization and the like. If you do that again, then we believe that by this natural selection, our population's overall fitness value will be increased. That's how we utilize this genetic algorithm in optimization. Okay. we'd like to minimize this function. And your feasible reason is integer from very simple. Your feasible reason is minus 100 to 100, and you'd like to find the minimum value of this objective function. Okay? So, first one is coding or formulation. I'd like to choose the binary coding. Because compared to the real coding, if I choose a chromosome with the real value, then all I need is one gene. X should be there. Then the problem is, it's quite not good to apply this crossover or mutation or such kind of operator. The probability of having better next generation with this genetic operator is, the longer your chromosome is, the possibility is higher. So that's why I choose the binary coding for this X. And we have to cover minus 100 to 100. So basically it's a 201 variable. How many bits do we need? Nope. Okay. If you guys don't help me, I will change the problem itself. Minus 31 to 32, 31, 32, 32, 32. Then we have to cover 64, right? Then, how many bits do we need? 6 bits. 2 times 6 is 64, right? Am I right, really? Okay. Then, which means our chromosome is 1, 2, 3, 4, 5, 6. We need that. Which is, but have to think very careful because we are covering minus as well. So there is some way to represent your thing. So our chromosome will work as one from 0, 0, 0, 0, 0, 0 to 1, 2, 3, 4, 5, 6, 1, 1, 1, 1, 1, 1. And this one is actually 0 in 10-based system, and this one is actually 64 in 10-based system. But in our own problem, we have to think of that this is actually representing minus 32, this one is 31. We need some kind of transformation system. But anyway, this is perfect chromosome design because it can represent all possible solution space, and it can represent completely represent the solution itself. So that's fine. Okay. Function evaluation. With this chromosome, can you evaluate that one? Yeah, I think so. if this chromosome is X, our new function is something like X in 10 base system minus 32. If you can calculate it, then we can, evaluate this function exactly, right? Okay. 3. The evolution process. There are many other approaches to perform the survival test, but most simple one is roulette wheel. Roulette wheel approach. There are famous TV show in KBS, One Day, Two Nights, and sometimes they spin this kind of, thing to determine their destination. Same thing here. Roulette wheel, that is a roulette wheel. It is for the random selection favoring those with best fitness to obtain a new generation of population N. Okay. I'd like to mention one more thing. What if there is a constraint? Well, same thing here. Let's consider minimization fx subject to some inequality constraint. Then the approach we have to take is penalty method because it's the simplest. So what we'd like to do is make us some function, something like this. Apply some penalty. If I make this kind of penalty function, it will dissuade the point not going out from going out of this boundary. It's a form of external penalty function, which we covered in Monday's class. And we have to define fitness Usually, even though we are minimizing some objective function in linguistical form, the maximum fitness means best one. Okay? So we usually transform our objective function into the fitness function, like this. Large fx if we maximize the fitness, then it will automatically minimize our objective function with constraint, right? Okay, I brought some example. Even though our feasible reason is like that, I made one more assumption that inequality constraint requires us that x should be greater than 0. So, anyway, one, two, three, four. Since we are only dealing with this positive number here, so let's forget about the front two for now. So 1, 1, 0, 0, 0, 1, 0, 0, 0, 0. Let's assume this is hypothetically randomly generated our first 4 chromosome, first population, and which translate this X is in 10 base system 13, 24, 10, 19, and fitness if you follow this one, you will have fitness value of yeah. For now, let's use this one as just fitness. 169. Okay. And sum of your fitness is like that. And percentage is, this is 169 base divided by this, which is 1401. Right? I think I'm accidentally maximizing something right now, but anyway, it is just good enough to explain the roulette system. And cumulative, because it's a percent, it's 0.1401, 0.6177, 0.7006, 1.000. It's 100% here. I think it's very straightforward. So given the randomly chosen first generation, you can always find this kind of table utilizing your objective function. Okay? The next thing of the roulette system is we are building a roulette wheel. Largest one first. Number 2. I don't know. Number 4. This is a roulette wheel. And from this one, we know that average fitness is of this population is 301, and best fitness is of this population is this one. And we can mimic this roulette wheel spinning process in computer simulation. Once again, utilizing random number generator. How? Utilizing this cumulative value. So, for example, do you know this normal distribution? It's bell-shaped curve in the average value. Looks like this, and this is probability density function, we call it, right? And we can easily transform this probability density function into cumulative density function, CDF. And it will look like something like this. This value is 0.1. Okay? So, usually your computer's random number generator usually generate a uniformly distributed random number. That is okay. And it can be easily transformed into the random number generator with normal distribution. But anyway, both ways are also possible. Depends on your problem. So, draw a random number from 0 and 1. Once you draw the CDF from 0 and 1, let's say you choose a 0.75, then you can read the value here, the x value here. And you can find the corresponding region here from this, right? By doing that, we can simulating spinning this roulette. The thing is, you know, we know this is the highest fitness value. This is the lowest fitness value. So really simple one is just to take the, for example, we have only survival rate of the 50%. We can choose these two because it's a best two. But that's not usually true in real world. The best one does not automatically survive. The best one has higher probability of survival. The best one, number 2, has the higher section. The second best one has the next higher probability. So that's why we are spinning this roulette for the survival test, right? And how can we spin this rule in the computer program? Well, you can use your random number generator, transform into CDF function, and then you can choose. You can generate the random number here and choose that. Yeah. Okay. Any question about this roulette survival test? Okay. There is another approach, tournament. This approach is also for the survival test. Tournament is widely used in sports event. Tournament. If you have, a team, you can randomly select pairs like this and compare these two with. So if this one has the higher or better fitness, this one survives here. And you do that again and again and choose whatever you want. Idea is really simple. Sometimes this unfair thing can happen, right? But that's the life. So genetic algorithm, we can do this one as well. So this is round 1, or this level is round 2. The number of rounds are all up to you. You can make 10 rounds out of 100 or something like that to really reduce the survival rate. Okay? If you have a much higher survival rate, you can reduce the round into number 1 or something like that. But anyway, selection of this pair is also randomly chosen. Okay? So if I write it in the formal manner, if I choose 2 rounds, this is kind of sample round. Randomly select a small portion from the total population and also choose a much smaller number of chromosome with best fitness. Run number 2. Assign achiever W a probability of selection based upon fitness and you can repeat as you want. Thing is like that. For round number 1, let's say this one has the fitness of 500 and this one has fitness of 1000. Then this one does not automatically survive. It will have 2 times of probability of survival compared to this one. So the roulette wheel will be like this. It has 2 times of a probability of being chosen. So anyway, run the random number once again, and sometimes miracles happen in a sports event. So this one can be survived. But anyway, probability, usually this one will survive. And this is the whole idea of this tournament selection system. Okay.